So the next topic we're talking about the model overfit and underfit. Okay, so let's take a look at this figure. Okay, so ideally, when you collect data, there should be a true function. Okay, so for example, right here, the true function is a distribution, okay, of x and y, and the true function is the blue line right here. But you know, when you collect data, okay, the collect data would not perfectly fit the true function. So the training data you get might be the black points, black dots right here. Okay, those black points is a little bit deviate from the true function, but it should follow the distribution of the true function. Okay, so that is okay. So and again, while we performing data analysis, we should have training data and testing data, right? So we can collect the data, the red points and the black points. And usually, you should we suggest that the black data point, training data, and the red data point, the testing data, they should collect it from the same population, right? The same population. But after that, okay, in when we analysis data, okay, in neural network, usually we will have the third set of data set, okay? The first one is the black one is the training data, okay? The second is called validation data. And the third one, okay, the red one is called testing data. And again, the data point right here is help us to try to find theta star. We have several different algorithms. We have different cross entropy function, MSE function. We minimize it or maximize it. Okay, by using MSE or cross entropy, we can find the optimized theta. We use training data to help us to find all those theta star value. Okay, but right here, when we talk about MSE with A and B, right? That is a basin, right? So we use gradient descent. We start from here and try to jump to the lowest point in MSE basin, right? But how many different steps you should take and when to stop? There are some algorithms that need to try to figure out when to stop and how to stop. And there are some other parameters, okay, which will not, we will use another set of data, which is the validation data, which is right here, to stop the process, okay? So every time when you find the value, okay, which is A T1 and T0 B T0, right? And you use gradient descent on training data to find the next step. Okay, so right here, AT1, BT1, right? But how did you know you should stop or continue to do gradient descent? Okay, you use the second set of data, which is the validation data, the blue data set right here, and you test. They use AT1 and BT1 to test the blue data set and to see what is the, for example, current accuracy or current MAC value. If the accuracy increase or the MAC value decrease, that means your parameter, okay, currently your parameter is better than the previous one, but you don't know if it is the best parameters, and you simply just use the black training data to perform gradient descent again to get AT2, BT2, and so on and so forth, Every time you get a new parameter, you use the blue data point, which is validation data set, to test against with your MSE value or maximum likelihood of cross entropy. If it is small enough, your MSE value, and you should stop to perform gradient descent by using the black data set. Okay, so let's say again, you use the black data set to perform gradient descent. You use the blue data set, validation data set, to test if you should stop or not. So after, for example, right, someplace right here, okay, you stop right here. So that is AT10, BT10. Okay, you decide to stop right here, and then you use the red data set, which is testing data set, to test your current model. So that is for testing. And that the accuracy right here, or the MSE value is the testing accuracy or testing MSE. That is the number you should report, not the accuracy of the black data set, or not the neither the accuracy of blue data set. You should report the accuracy of testing data set. Okay, that is the your accuracy, your MSE value. And make sure when you collect those data sets, they should not overlap. You cannot use validation data set to train to perform partial differentiation in gradient descent. You should not use your testing data to train your model. You can only use black training data set to do so. Okay, so make sure you understand that. Okay. So again, okay. If we so that is right here. So again, the true function is the blue one, and you use the observations, which is your training data set, to train your data. Okay, if your model is too simple, so that is degree 1, that means it is a linear regression. Okay, you can output this value, output this regression model, okay, this line. But as we can see that it is not appropriate. Okay, so that is what we call underfit. Okay, so if you use more complex model, for example, degree 25, and if you have, that is AX25, B, oh sorry, AX25 plus BX24, CX23, and so on and so forth, YX plus Z. If your model is so complex, and that means you can have a lot of different turning point, okay, to match your data. For example, right here, this black observation training data is a little bit far away from its true value, from the true function, right? But because your model is so complex, so your model will try to make a turn right here to fit the black observation. But that is too much, okay? That is too much, okay? So we call it overfitting. The model will try to memorize. There is a data point right here. They are not going to generate a general model to fit a true function from the observations. Okay, so that is what we call overfitting. So in this case, okay, there are some points which is not that good when you do testing. Okay, so the balanced model is AX5, BX4, something like that. Okay, the balanced model is like that. Okay, but when you evaluate different models, okay, so that is a degree. So it indicates the complexity of your model. the complexity of your model. If you have more parameters to describe your model, okay, so that is here, okay, and here is the validation, right? So we perform we perform validation by using the validation test, and that is the error value. And as you can see that if your model is too simple, for example, right here, we will get a very high error. And you have a proper, so that is underfit. This side, okay? That is a proper. And at the right hand side, you can see that you have a very high degrees of model, which means your complexity of model will be quite high, and we call it overfit. Because you have too many parameters, those parameters can memorize your data point, but too much, okay? Too much. Okay, so you can always draw a figure like this to see if your model is overfit or underfit, okay? And we can see that if you use your testing data and training data, you can see that even though your training data can have a very low errors, but that means your model remember what your data is, and that would damage, okay, your generalization of your model. So we can see that using testing data or using validation data, you can see that there's overfit, and the proper value should be right here, something like this one. Okay, and here we have underfit. That means your model has too less parameters to model your data. Okay, so that is. So in order to fix this problem of overfit and overfit, okay, we have another strategy called regularization. Okay, we will show you how to perform regularization by using orange, but I'd like to show you some theory right here. Okay, again, okay, the blue lines, okay, is the training sample. Okay, if the model complexity from low to high, okay, and that is the prediction error. Okay, if since, so that is called underfit, and that is called overfit. That means if your model is too simple to describe the data you have, the error will be high, so that is right here. But after you gradually increase the complexity of your model, and of course, because the model is so complex, so it can remember the data point you provide, so the error will gradually decrease to a very low level, right? Because you can train your model to find the exact relationship between every data point. But in the meantime, you should use a test data set or validation data set right here. You should test your model by using another set of value, another set of data. Okay, validation data set or test data set, and I suggest using a validation data set. And you can see that right here. It seems like at this point you have a low error on both training data set and validation data set. But if you use a more complex model to overfit this data, and this model will try to remember all the data points in training data set, and the generation will be corrupt, and that means when you use validation data set to test the error, it gradually decrease. That is not a good situation. So again, we suggest when you build your model, try validation data set every time. Okay, and you can see that the error will gradually decrease. That means everything good, still good. But if you see the error increased on validation data set, and that means your model is overfit. So the next one, we continue to talk about the overfit. There are two important regression called ridge regression and lasso regression. They can help us to figure out if your model is overfit and is overfit. It has a very interesting function right here, okay? And you can see that is the MSE, right? And that is exact ridge regression. So by adding another item right here, so that is, for example, if your model is y ax plus b, so basically your MSE value, okay, should be like this, right? That is your MSE value. But we not only minimize the MSE, we also minimize, okay, there's a lambda right here, okay? We also minimize this value. And the lambda right here is the weight, okay? It's the weight. You should define the weight, okay? So that's also, we try to minimize this value. Okay, so in this case, the ridge regression. Okay, we take a look at the lasso right here again. Okay, and again, right here. So that is to minimize the MSE value plus a and absolute value of b. Okay, with lambda. Okay, so by using this one and this one, we are trying to shrink the coefficients, and it can help to reduce the model complexity and multicollinearity. And again, when lambda is 0, the cost function becomes similar to linear regression. Okay, so that is just a weight. Okay, and right here, for ridge regression, okay, because there's a part 2 right here, so we also call it L2 regression, okay, and because that is absolute value, so lasso is also called L1 regression, okay. So according to some complex mathematics, okay, L1 regression can lead to 0 coefficient. That means when you perform lasso regression, sometimes the value of A or B will become 0. So if the model looks like this, so if A or B becomes 0, or the model can be very complex, something like that. So if part of the coefficient becomes 0, that means this model will be less complex, right? Because if you have more parameters in your model and your model is more and more complex, so if you have less parameters and your model become more simpler, right? So if you apply lasso regression in your optimization function, sometimes the coefficient right here will become 0. So it makes your model become simpler. So it indicates that if you use lasso regression, your model will not overfit sometimes because it has less parameters to model your data. And of course, it depends on the weight you put right here, and it depends on your data. Okay, but we would say that if you use lasso regression to replace your MAC, and your model would become would not overfit, would not that overfit. Okay, they have some. I write some explanation right here by using mathematics, but it depends on you to go over those mathematic details. Okay, so here is an example. Okay, we generate some data point by using this y equals 1.2x plus 0.7. Okay, and we can see that some randomness in this generated data. Okay, so the first thing is that this one. Okay, we use original MSE. Okay, to plot this. Okay, thing right here. If you are interested in plot contour graph, okay, contour line, okay, that is contour line, okay. So that is the basin of your MSE value, okay, your MSE value. So you can see that that is the lowest data point, lowest MSE value, and its value is 0.0047, right? And its corresponding parameter, okay, we call A star and B star, right? Okay, sorry, B0 should be B, A, B1 should be A, right? So that is the B star, A star will be this value, okay, will be this value. Okay, it is not 0.7 and 1.2. That is because we generate data with some randomness. So the best MSE value is not at 0.7 and 1.2, but it really doesn't matter. Okay, and we can see that this contour line, okay, that is the smallest MSE, and we have a larger. So it is a basin, right? It is a basin. So if we apply lasso and ridge regression, okay, on this data set, okay, we can see that for lasso, lambda equals 1, okay, we can see that the lowest data point is right here, okay. Lasso is MSE plus sigma theta j belongs to theta j, okay, because it's a lasso, right? So that is the absolute value, and we can see that the entire value right here, okay, it moves to this data point, okay. So originally the lowest MSE point would be here, but if we change the cost function and the shape changes, okay, you can see that the contour line changes, right? So the lowest point will be right here, the lowest value of MSE plus this value, okay, should be right here, okay. And again, for ridge regression, okay, it moves to here, okay. But before we but I would like to show you talk more about ridge regression and lasso regression by using this figure, because this figure is very popular on the internet. If you Google lasso or ridge regression, you can see this figure. So I'd like to show you how to read this figure, okay. So here we have B and A, okay, parameters. So that is the basin, okay, the contour of the MSE value. So MSE plus sigma theta square, right? So that is, so this part will be this part. Okay, so that is the contour line, right? Non-contour line. So the contour line would you can draw the line. Okay, so maybe there's one line like this one. Okay, we put it right here. So again, that is the lowest point, right? So we can simply draw a line. Okay, so let's take a look at this one. Okay, the theta square. So that should be a squared plus b squared. And as you can see that in that plan, a squared plus b squared, that is an circle, right? So if you simply just random select one point right here, so that is 1a and b, a1 and b1, okay? A random point on the circle. And a1 squared plus b1 squared. The result would be this one, okay? So that means r, the radius, okay, equals to radius squared. Okay, no matter this point is a1 b1 or this one a2 b2 or a3 b3, it really doesn't matter, because in the same circle, okay, all the points on the circle, they have the same radius. Okay, so the a squared plus b squared equals to r squared. Okay, no matter which point it is. Okay, so again, we can further draw a circle which touch the this data point, this point. Okay, this point. Okay, so think about one thing. Okay, at this point, it has smallest MSE value, but think about one thing, it has a very large radius. Okay, and RA, right? Okay, and think about another point right here, the green one. It may have a larger MSE value because this value is on that contour line, right? It has a large MSE value, but the radius is 0 at this green point, right? So it's a squared plus b squared equals 0. Okay, think about one thing. That has the smallest MSE but larger radius. It has a larger MSE but 0 radius. So there should be one data point between the blue dot and the green dot, which has larger MSE and smaller radius. But when you combine them together, there should be some data points right here. It has the smallest cost function. Okay, think about these things. So that is how you read this figure. Okay, there should be one point between the lowest MSE and the 0 point, and it has the smallest cost function value. It is neither the one with smallest MSE or neither the one with smallest radius. It is some sweet spot between blue point and green point. Okay, it's the same for lasso regression. Okay, for lasso, okay, we have a plus b, okay, with absolute value. When you do so, you simply just find and again, there should be some contour line which touch the 0 point. Okay, and there should be some square. Okay, it is not a circle anymore. Okay, it is a square. Okay, so for all those data points in this, so for the blue points right here, again, it has the smallest MSE value, but it has a very large square, right? And for the blue data point, blue points, it has a very small square, zero square. Okay, it has a zero. It is a point, so it has no square right here, but it has a large MSE value. But there should be some data point which has smallest cost function. It's the same. Okay, just because we use the square right here, so we use a circle right here. Because we use the absolute value right here, so we draw a square right here. That's how you read this figure. Okay, and again, we can use some data right here, but we will show you how to do it in orange. Okay, we start right here.